Many types of equipment, such as pumps, agitators, or mixers, have rotating shafts that extend from a stationary housing. In nearly every case, some material or device is needed to seal around the shaft to prevent fluids or lubricants from leaking out and to keep contaminants from getting in. Some equipment has packing material to seal around the shaft. Other equipment has a more sophisticated device known as a mechanical seal. A mechanical seal is basically a device that is composed of two separate parts, one that mounts to the rotating shaft and one that mounts to the stationary housing around the shaft. When the shaft rotates, the rotating part of the seal spins so close to the stationary part that leakage around the shaft is virtually eliminated. There are many types of mechanical seals, and they can be used in many different situations. As a mechanic, you'll need to understand how these seals work and how they're installed. In this program, we'll spend some time examining mechanical seals. We'll see how mechanical seals operate, what needs to be done before a mechanical seal is installed, and how to install different types of mechanical seals. Then later in the program, we'll look at some examples of mechanical seal failures. Since one of the most common uses for mechanical seals is in process pumps, we'll use that equipment as an example throughout this program. But before we examine how a mechanical seal works, let's first look at some of the basic parts of a mechanical seal. Many people consider mechanical seals to be very complex due to the number of internal parts. Actually, mechanical seals are relatively simple. From this cutaway of a typical mechanical seal, we can see the two basic elements, known as the rotating element and the stationary element. This rotating element, which mounts on the pump shaft and rotates with it, consists of a collar, set screws, a spring, and a rotating ring. The collar and set screws are used to mount the rotating element to the pump shaft. The collar also provides a point for the spring to work against. The spring is used to hold the rotating ring in its proper position. The rotating ring has a lapped and polished surface, which is called the rotating seal face. The stationary element mounts to the casing that surrounds the rotating shaft. This part of the seal remains stationary and works in conjunction with the rotating element. This stationary element consists of a gland plate and a mating ring. The gland plate is a metal plate that mounts to the stuffing box of the pump. It is also the part that the mating ring mounts to. The mating ring also has a lapped and polished surface. This surface is the stationary seal face. The stationary seal face and the rotating seal face work together to form the primary seal. This area is perhaps the most important sealing surface inside a mechanical seal. The condition of the rotating seal face and the stationary seal face is critical. Both of these surfaces have been lapped and polished to near perfection, and any imperfections could seriously affect the seal's performance. Mechanical seals can be made from a variety of materials. The type of material used depends on the conditions that the seal must operate in, such as temperature, pressure, and the corrosiveness of the fluid being sealed. For example, the collar, spring, and gland plate are normally made from materials that are highly resistant to corrosion, such as stainless steels, brass, or other alloys. The seal faces are usually made of materials like tungsten, ceramics, or different grades of carbon. Seal face surfaces made from these types of materials generally last longer. Also vital to a mechanical seal's operation are O-rings, bellows, and gaskets. Although these items are simple, they serve important functions. There are several places inside a mechanical seal where fluid could leak. The most noticeable spot is the primary seal surface, which is between the rotating seal face and the stationary seal face. But there are other points, such as around the shaft or casing, that have to be sealed as well. These points are normally sealed with O-rings, bellows, or gaskets. For example, the area between the mating ring and the gland plate is often sealed by using an O-ring or gasket. This seal prevents fluid from leaking around the stationary element of the seal. The area between the rotating element and the pump shaft is commonly sealed with a bellows. This seal prevents fluids from leaking under the rotating element and escaping past the seal faces. The type of sealing device used inside a mechanical seal can vary. For example, on some rotating elements, the bellows is replaced by an O-ring. Now that we've identified the basic components, let's take a look at how a mechanical seal works. When the pump is not operating, the components of the mechanical seal are idle. The spring inside the mechanical seal holds the rotating seal face against the stationary seal face. This prevents leakage while the pump is shut off. When the pump starts, the rotating element begins to turn. At the same time, pressure inside the pump begins to build. As the pressure increases, fluid is forced between the two seal faces. This thin layer of fluid measures only a few 100,000ths of an inch in thickness and serves two purposes. First, it helps keep the seal faces separated, and secondly, it provides lubrication for the faces. Normally, this fluid is the same as the fluid being pumped, but in some cases, fluid is supplied to a seal by an external source. This fluid is also known as a flush. A flush can be supplied to a seal in a number of ways, but regardless of how it's done, the purpose is to lubricate and protect the seal faces. For example, suppose this pump moves a fluid that contains abrasives. There's a possibility that abrasives from the fluid could get between the seal faces. If that happened, the mechanical seal faces could quickly be damaged or ruined. One way to avoid this damage would be to use an external fluid source. Now, whether a seal uses the fluid being pumped or an external fluid source to lubricate the seal faces has little to do with the basic operation of the seal itself. All mechanical seals work on the same basic principles and can be divided into two basic categories: pusher type and non-pusher type. This is a cutaway of a pusher type seal. A pusher type mechanical seal is one in which the rotating ring and the seal located between the rotating ring and the shaft are free to move along the shaft. In other words, the seal slides along the shaft with the ring. A non-pusher type mechanical seal uses a different approach. The rotating ring moves as necessary, but the seal between the ring and the shaft is independent of this movement. Instead of sliding along the shaft, the seal, which is typically a bellows, expands and contracts to prevent leakage. While there are two basic categories of mechanical seals, most seal manufacturers produce a variety of each. These include inside, outside, and multiple seal arrangements. An inside seal is one of the most common arrangements of mechanical seals. A typical inside seal has the rotating element located inside the casing that's being sealed. An outside seal has the rotating element mounted outside of the casing being sealed. While the components are generally the same as those of an inside seal, the outside seal installation is different. Another type of mechanical seal arrangement is the multiple seal. A multiple seal is basically two or more seals mounted so that they work together. Multiple seals are sometimes used on pumps that move hazardous fluids because they further reduce the chance of a fluid leak. There are three common types of multiple seals available: the double seal, the opposed double seal, and the tandem seal. A double seal has two stationary elements and a single rotating element. The rotating element has two rotating rings separated by a spring. Each ring has a lapped and polished face that works in conjunction with the two stationary seal faces. Another type of multiple seal is known as an opposed double seal. An opposed double seal has two rotating elements and a single stationary element. The opposed double seal gets its name from the fact that the two rotating rings work against opposed sides of the mating ring. The third type of multiple seal is the tandem seal. A tandem seal is basically two independent seals mounted together. Each tandem seal has its own rotating element and stationary element. Many inside, outside, and multiple seal arrangements are available as cartridge seals. Cartridge seals are designed to make seal installation easier. As you can see, the components of a cartridge seal are mounted onto a sleeve. By having the components pre-assembled, the time spent installing the seal is usually less than that of other seals. Before any mechanical seal can be installed, certain preparations have to be made. When we come back, we'll see how to prepare for a mechanical seal installation by watching the disassembly of a process pump. But first, take some time to review the material in the text and to answer the questions at the end of the segment. In the previous segment, we examined the components of a mechanical seal and saw how a typical mechanical seal worked. In this segment, we'll see how a typical process pump is disassembled so that a mechanical seal can be removed and replaced. As the procedure takes place, some general precautions should be followed to ensure that the seal can be installed properly. For example, the work area and the pump housing should be cleaned. Company policies and procedures should be followed, and all old gaskets should be replaced. The pump we'll be disassembling is a typical process pump. From this simplified cutaway, we can see the major components. This is the pump casing, the impeller, the backplate, which forms the stuffing box, the pump frame, which connects the pump casing with the bearing housing, and the pump shaft. The mechanical seal will be mounted here, inside the stuffing box. In many cases, the mechanical seal mounts onto a shaft sleeve, like the one seen here. The shaft sleeve protects the shaft from the mounting hardware of the mechanical seal. Now that we've identified the components, we're ready to start the disassembly. We'll begin the procedure at the point where the pump has been tagged out according to company procedures and moved to a shop. One of the first things to do is to separate the casing from the pump frame. In order to do this, the casing bolts must first be removed. Once the bolts are out, the casing and pump frame can be forced apart by installing jacking bolts. These bolts are turned in a crossing pattern to evenly dislodge the casing and frame. With the casing and frame separated, the frame and bearing housing can be moved to the side to allow for easy access to the remaining parts. The jacking bolts can also be removed. Then the old casing gasket can be removed and discarded. A new gasket will be installed later. Next, the impeller can be removed. The small impeller gasket can then be removed as well. The pump backplate should then be match marked with the frame before it's removed. Match marking these components with a marking pen of some sort makes reassembly and alignment easier. In order to remove the backplate and the gland plate, the nuts that hold the backplate to the frame are first removed. Next, the nuts on the gland studs are removed and the gland plate is moved back out of the way. The backplate can then be removed and set aside. This exposes the shaft sleeve and the rotating element of the mechanical seal. Then the shaft sleeve and seal can be slid off of the shaft, along with the gland plate. Then the mating ring can be removed from the gland plate by simply pushing it out. The collar set screws for the rotating element can be loosened and the element slid off of the sleeve. That takes care of the first part of the process. The pump has been disassembled and the old mechanical seal components have been removed. Now, certain checks and measurements must be made before the new seal is installed. One of the first things to do is to check all machined surfaces for nicks and burrs. Surface defects on the frame, gland plate, stuffing box housing, shaft, or sleeve could result in leaks and damaged components. Minor imperfections in these machined surfaces can usually be removed with a small file or crocus cloth. Some pumps rely on metal-to-metal contact instead of a gasket or O-ring to seal between the shaft shoulder and the sleeve. On these units, the surfaces should be lapped to remove imperfections and create an acceptable seal. First, the shaft key is removed and lapping compound is applied to the shaft shoulder. Then the sleeve is placed on the shaft and turned. After a few minutes, the sleeve can be taken off and the lapping compound removed. The surfaces can then be inspected to make sure that the proper surface contact can be made. The drive pins or keys and their alignment slots should also be inspected for signs of wear or damage. Damaged pins or keys could cause the shaft sleeve to move on the shaft and damage the seal and the pump components. There are other important checks that should be made before a mechanical seal is installed. Some of these checks involve the use of dial indicators to make precise measurements of the pump. One important check is testing for shaft runout. A shaft that is bent or out of round can damage other pump components and make a mechanical seal virtually worthless. One way to check for shaft runout is to mount a dial indicator to the pump frame, with the indicator button touching the surface of the shaft, perpendicular to the shaft's axis. The dial indicator is then zeroed and the shaft rotated. The dial indicator should measure any shaft runout present. Excessive runout will prevent the seal from functioning properly. To determine if the runout measured is excessive, you'll need to refer to your company's policies and procedures or to the manufacturer's specifications. The process should be repeated with the shaft sleeve and the impeller in place to check for sleeve runout. Excessive sleeve runout could also cause serious problems. Once the sleeve runout check is complete, the impeller and sleeve can again be removed from the shaft. Dial indicators can also be used to check the wear of both the radial and the thrust bearings that support the shaft. To check radial bearing wear, a dial indicator is mounted above the shaft with the indicator button touching the top of the shaft. The shaft is then carefully lifted and the dial indicator measures any radial movement. Excessive radial movement could indicate worn bearings. Once again, you'll need to refer to the manufacturer's guidelines to determine if the amount of radial bearing wear is acceptable. One way to check the thrust bearing wear is to mount the dial indicator so that the indicator button is touching the end of the shaft. The dial indicator is set to 0 and the shaft is moved back and forth. The dial indicator will measure the total movement of the shaft. Excessive axial shaft movement could be an indication of worn thrust bearings. The final check using a dial indicator involves checking the machined surface of the pump frame to see if it's perpendicular to the shaft. Since the pump back plate, which also forms the stuffing box where the mechanical seal components fit, mounts directly to this frame, it is essential that the frame is perpendicular to the shaft. Checking the frame is done by mounting a dial indicator on the shaft so that the button touches the machined surface of the frame. With the dial indicator zeroed, a mark is made at the starting position and the shaft is rotated. A reading is taken at the 12 o'clock, the 3 o'clock, the 6 o'clock, and the 9 o'clock positions. If the frame surface is not perpendicular to the shaft, then the back plate and the stuffing box will be misaligned as well. And misalignment of these components could cause premature seal failure. Now, it's important to remember that any shaft adjustments or repairs that are necessary must be made before the mechanical seal is installed. Adjustments that are made after the seal is mounted could easily alter the position of the rotating element and cause serious seal damage or failure. So far, we've seen how to disassemble a pump and make all the necessary checks and measurements so that a mechanical seal can be installed. When we come back, we'll continue the process by looking at how to install an inside pusher seal. In the last segment, we saw how to disassemble a process pump and remove an old mechanical seal. Now we're ready to install a new mechanical seal, in this case, an inside pusher seal. As you recall, an inside pusher seal mounts inside the pump casing. And again, the components can be broken down into two separate elements, the rotating element and the stationary element. Once all the preliminary checks that we discussed earlier have been made, the seal installation can begin. Now, the procedures we'll follow could be slightly different from the ones you'll use because of differences in seal applications and company policy, but the general principles should still apply. In the first part of the installation, some of the pump components are assembled so that measurements can be taken. These measurements are used later to position the components of the mechanical seal. Since this pump is equipped with a shaft sleeve, one of the first steps is to position the sleeve onto the shaft, making sure that the sleeve is properly engaged on the drive pins or keys. An improperly positioned sleeve could be damaged or ruined when the impeller is installed. This shaft sleeve has a small lip that butts against the shaft shoulder, where the shaft threads begin. This lip is sandwiched between the impeller and the shaft shoulder when the impeller is installed later. Once the sleeve is in place, the pump backplate is positioned onto the frame. The match marks between the backplate and the frame should be checked to make sure that the backplate is properly aligned. Once the backplate is in place, the nuts that hold it onto the frame should be tightened evenly. Next, the impeller is installed. Once the impeller is in place, the clearance between the impeller and the backplate should be checked to ensure that the impeller is properly positioned. Since the impeller on this pump holds the shaft sleeve in place, if the impeller is out of position, the shaft sleeve and the mechanical seal components could be out of position as well. And if these components are out of position, the mechanical seal could fail. Here, the pump manufacturer's prints are checked to get the proper clearance figures. Then a feeler gauge is used to check the gap between the impeller and the backplate. The feeler gauge reading can then be used to determine if the impeller is properly positioned. After the impeller clearance has been measured, the shaft sleeve has to be marked so that the rotating element can be positioned later. This is done by first applying bluing to the shaft sleeve along the edge of the stuffing box. Then a line is scribed in the bluing to mark the end of the stuffing box. This becomes a reference line for positioning the rotating element. Once the line is marked, the pump components can be disassembled again. First, the impeller is taken back off. Then the nuts that hold the backplate in place are removed, and the backplate is taken off of the pump frame. Finally, the sleeve is removed from the shaft and additional bluing is applied, this time along the length of the sleeve. Next, the pump or seal manufacturer's prints are checked to get the figure used to determine where the rotating ring collar will be mounted on the shaft sleeve. This figure, also known as the location dimension, is then used to measure along the sleeve from the line marking the edge of the stuffing box. At that point, a second line is scribed in the bluing. Once the measurements have been made and the mark has been scribed in the sleeve bluing, the second part of the installation process can begin. First, the mechanical seal components, which include new gaskets and O-rings, a mating ring, and an assembled rotating element, can be inspected for damage. Once the parts have been inspected, a small amount of lubricant is applied to the shaft sleeve. Next, the rotating element is slid onto the shaft sleeve. The end of the rotating element collar that is opposite the seal face is then aligned with the second scribe mark. If the rotating element is not properly aligned, the seal could fail prematurely. Next, the set screws on the collar are tightened just enough to hold the collar in place. If the set screws are over-tightened, the sleeve could become oval-shaped and may not fit on the shaft properly. The screws will be tightened the rest of the way later when the sleeve is installed on the shaft. Many seal manufacturers use retaining clips, like the one seen here, to compress the springs and hold the parts of the rotating element together before it's installed. Once the rotating element has been secured to the sleeve, these clips can be removed. The next step is to prepare the mating ring for assembly into the gland plate. First, the gland plate should be wiped clean with a rag. Then the O-ring can be installed onto the mating ring. Next, the gland plate is lubricated to make the mating ring installation easier. As you recall, the mating ring has a polished side and an unpolished side. Most manufacturers mark the unpolished side of the ring so that it can be told apart from the polished side. The mating ring is inserted into the gland plate so that the unpolished side goes in first. This will allow the polished side of the mating ring to face toward the rotating seal face once it's installed. The mating ring should be fully inserted into the plate and must not be cocked to either side. The gland plate can be turned over so that the back side of the ring can be checked to ensure that the mating ring is properly situated. Once the mating ring is in place, all excess lubricant should be removed with a clean cloth. Also, the mating ring face should be cleaned with lens paper and an approved solvent. Then the gasket between the gland plate and the stuffing box is positioned on the gland plate. and the gland plate is slid onto the shaft and pushed back against the bearing housing out of the way. Then the rotating seal face is wiped clean with lens paper and an approved solvent. And the shaft sleeve, which has the rotating element mounted on it, is slid onto the shaft. The gland plate should be supported while the sleeve is installed, and the sleeve should be pushed back until the sleeve lip is flush with the shaft shoulder. Again, make sure that the keyway on the sleeve lines up with the pin or key on the shaft. Once the shaft sleeve is in place, the set screws on the rotating element collar, which were simply snugged earlier, can be tightened down completely. Next, the back plate, which includes the stuffing box, is placed onto the frame. The back plate should be properly aligned with the frame match marks, and the stuffing box studs should align with the gland plate. Then the nuts that hold the back plate in place should be tightened. Now the impeller can be readied for installation. On this pump, a small O-ring is used to seal between the impeller and the shaft sleeve. Once the O-ring is in place, the impeller can be installed. Again, the clearance between the impeller and the back plate should be measured with a feeler gauge and checked against the pump manufacturer's specifications. If the reading is unacceptable, it could be an indication that the shaft sleeve and rotating element are improperly positioned. Any indication of a problem should be investigated to prevent premature seal failure. Once the gap between the impeller and the back plate has been checked, the gland plate should be slid along the shaft toward the stuffing box. The gland plate nuts are then installed and tightened until the gland plate is snug against the stuffing box. Over-tightening these nuts could warp and damage the mating ring. To ensure that the nuts have been uniformly tightened, the gap between the gland plate and the stuffing box is measured at each gland plate bolt. If the gland plate is properly installed, each reading should be the same. The installation of the mechanical seal is now complete. The remaining pump components can be reassembled and the unit can be returned to service according to company procedures. As you know, an inside pusher seal is just one type of mechanical seal available, and there are other methods of installation as well. When we return, we'll see how to install two other types of mechanical seals. In the previous segment, we saw how a typical inside pusher seal is installed. In this segment, we'll look at a couple of non-pusher type inside seals. First, a typical elastomer bellows inside seal, and then a metal bellows seal. We'll begin by looking at an illustration of a typical non-pusher elastomer bellows seal. Here's the rotating element, which consists of a collar with set screws, a single spring, a rotating ring, and the elastomer bellows. The stationary element is simply a gland plate and a mating ring with an O-ring that fits into the gland plate. You'll recall that the major difference between a pusher seal and a non-pusher seal is the arrangement of the seal between the rotating element and the shaft. While a pusher seal has an O-ring or a wedge to seal this area, a typical non-pusher seal has a bellows. This bellows expands and contracts to seal between the rotating element and the shaft. The expansion and contraction of the bellows also allows for axial movement of the rotating element in the shaft. Another difference between the pusher seals that we saw earlier and this non-pusher seal involves the rotating element spring. This seal has a single spring, whereas the other seals had a set of springs. Now, the installation of the non-pusher seal is very similar to that of the pusher seal that we saw earlier. The major difference is in how the rotating element is assembled onto the shaft sleeve. We'll begin the installation procedure from the point where the shaft sleeve has been blued and marked to indicate the edge of the stuffing box. In other words, all of the preliminary steps have been done, and the seal installation is ready to begin. As before, the manufacturer's print should be checked to get the location dimension, which is used to position the rotating element. The figure is then used to measure along the shaft sleeve from the line marking the edge of the stuffing box. At that point, a second line is scribed. The collar for the rotating element is then slid onto the sleeve so that the end of the collar opposite the seal face is positioned at that second line. The set screws are partially tightened so that the collar is held in place, and the spring is positioned on the sleeve. Then a small amount of lubricant that's approved by the seal manufacturer is applied to the outside of the sleeve. What happens next is different from what we saw before. As the rotating ring is placed onto the sleeve, the elastomer bellows makes contact with the lubricant and causes a bonding action between the bellows and the sleeve. Because of this, the rotating ring must be properly positioned against the spring as quickly as possible before the material bonds itself too tightly. Once the rotating ring has been positioned on the shaft sleeve, the remaining steps are basically the same as the ones we saw for the pusher seal. As you've seen, the non-pusher seal and the pusher seal share some common components, and many of the installation procedures for these two types of seals are the same. But because of certain design features, the elastomer bellows seal has a few advantages over pusher-type seals. For example, since the bellows of the non-pusher seal bonds to the shaft sleeve, there is no movement between the bellows and the sleeve. As a result, there's less of a chance that it will leak. Because many non-pusher seals are equipped with elastomer bellows, some can only be used in moderate temperature and pressure ranges. However, there's one type of non-pusher seal that is designed for high temperature and pressure ranges. That's a metal bellows seal. The components of a metal bellows seal can be made from a variety of materials which make it possible for the seal to be used in temperatures ranging from around -100 degrees Fahrenheit to around 800 degrees Fahrenheit. One of the most noticeable features of this seal is that it uses a flexible metal bellows instead of a spring. This bellows expands and contracts to compensate for axial movement of the shaft and for seal face wear. It also seals between the rotating element and the shaft like the elastomer bellows did in the example we saw earlier. The bellows can be a single piece of metal shaped into a bellows, or it can be a series of metal plates welded together. Either way, one end of the bellows is welded to the collar, and the other end is welded to the rotating ring. Another difference in this metal bellows seal is in the design of the collar. You'll notice that there are two sets of screws. One set is used to hold the rotating element in place, like the ones we saw earlier. The other screws are used to compress a gasket located here, which also seals between the rotating element and the shaft. There's another added feature on this seal, an auxiliary bushing. The main function of this bushing is to direct any leakage from the primary seal to an outlet or discharge area. It's held in place on the gland plate with two small bolts. With the exception of a couple of steps, the installation of a metal bellows seal is basically the same as the procedures we saw before. Once again, we'll begin the installation procedure after all the preliminary checks have been done and a line has been scribed to mark the end of the stuffing box. Once the location dimension has been found on the manufacturer's prints and a second line has been scribed on the shaft sleeve, the rotating element is installed, and the set screws are partially tightened to hold the collar in place. Next, since this type of seal uses a gasket to seal around the shaft sleeve, the cap screws on the collar are tightened to compress the gasket. These screws should be tightened in a crossing pattern so that the pressure against the gasket is even. Now, the next steps are the same as we saw earlier. First, the gasket for the mating ring is inserted into the gland plate, along with the mating ring itself. Then the gasket that seals between the gland plate and the stuffing box is placed on the gland plate, and the gland plate is slid onto the shaft. Next, the shaft sleeve is positioned on the shaft, and the collar set screws are tightened the rest of the way. Once the sleeve is in place, the pump backplate is installed. Then the impeller is installed, and the clearance between the impeller and the backplate is checked to make sure that the components are properly positioned. Once the impeller clearance has been checked, the gland plate is bolted to the stuffing box, and the gap between the stuffing box and the gland plate is measured to ensure that the gland plate bolts have been properly tightened. The final step is different from what we've seen before. The auxiliary bushing that we looked at earlier should be secured by tightening the two mounting bolts. Once that's done, the seal installation is complete. The pump can now be reassembled and returned to service. In this segment, we examined two types of non-pusher mechanical seals, an elastomer bellows seal and a metal bellows seal. We saw how they differed from the seals that we looked at earlier, and we saw how they're installed. When we come back, we'll take a look at two more types of mechanical seals, an outside seal and a cartridge seal. Up till now, we've seen how to install a pusher-type seal and a couple of non-pusher-type seals. Now we'll examine the installation of an outside seal and a cartridge seal. In general, outside seals are among the simplest types of mechanical seals. You'll recall that outside seals are mounted outside of the pump casing. As a result, they're generally easier to install. Let's begin by looking at the components. Here we see the two familiar elements, the rotating element and the stationary element. While the mating ring and gaskets are basically the same as those in other types of seals, a few of the components are different from what we've seen before. On the seal that we'll be using, the bellows that's used to seal between the rotating ring and the shaft is made of a different material. This material allows this seal to be used in more severe applications than the elastomer bellows type. The rotating seal face is also different. In this seal, the rotating seal face is a replaceable carbon ring. Also, there are no collar set screws. Instead, the collar itself is a clamp-like ring with two small bolts. These bolts are tightened to secure the collar to the shaft. There's also a bushing that fits into the stuffing box to help prevent debris from entering the seal and to reduce the amount of external lubricating fluid that escapes. The bushing is held in place with a small screw. The pump we'll be using has no shaft sleeve. As we begin the installation, the preliminary checks have been completed. The shaft has been blued and a line has been scribed to mark the edge of the stuffing box. By using the location dimension found in the manufacturer's prints, a measurement is made from the first line. This time, however, the measurement is made in the opposite direction, away from the impeller end of the shaft. A second line is then scribed at that point. Once the second line is scribed on the shaft, the rotating element can be placed on the shaft and slid back against the bearing housing. Next, the stationary element is prepared for installation. This is done by first installing a gasket into the gland plate, then installing the mating ring. On this seal, the polished face of the mating ring is installed so that it will face away from the stuffing box. Then a second gasket is installed, and the gland plate assembly is ready to be installed onto the shaft. As the gland plate is installed onto the shaft, it should be slid back as far as possible and positioned against the rotating element that was just installed. With the rotating element and the stationary element on the shaft, the back plate can be prepared for installation. First, the bushing that was mentioned earlier is inserted into the stuffing box and secured with the screw. Then the back plate can be installed on the pump frame. Next, the gland plate can be slid into position and the cap screws tightened. Then the gap between the gland plate and the back plate is checked with a feeler gauge to ensure that the gland plate was properly tightened. Once that's done, the rotating element can be positioned so that its collar is aligned with the second scribe line on the shaft. Then the clamping screws can be tightened. Once the rotating element is in place, the impeller can be installed and tightened. The clearance between the impeller and the back plate should be measured with a feeler gauge and compared with the manufacturer's specifications to ensure that the components have been installed correctly. The seal installation is now complete, and the pump can be reassembled and returned to service. The installation of the outside seal was somewhat different from the earlier examples. Our next example, a cartridge seal, is different as well. This particular cartridge seal is a multiple seal That is, there are basically two seals mounted in series. Each seal has its own rotating element and stationary element. But there is one feature of the cartridge type seal that differs from the other types. The components of a cartridge seal are pre-assembled onto a sleeve and gland plate. This reduces the time necessary to install the seal. The shaft sleeve also includes a collar, set screws, and an O-ring. The collar and set screws are used to hold the sleeve in position on the shaft, and the O-ring prevents fluids from leaking out between the shaft and the sleeve. Now let's see how the seal is installed. As before, we'll begin the installation after the pump has been disassembled and all preliminary checks have been completed. First, the cartridge is slid over the shaft and positioned so that the drive pin engages the slot on the cartridge sleeve. Then the back plate is aligned and positioned against the pump frame and bolted into place. Once the back plate has been secured, the gland plate can be bolted to the stuffing box housing. The bolts should be tightened using a crossing pattern so that all the bolts are tightened evenly. Then the clearance between the gland plate and the stuffing box is checked with a feeler gauge at each bolt to make sure that the bolts were tightened evenly. Once that's done, a new gasket is placed on the impeller, and the impeller is installed. With the impeller in place, the gap between the impeller and the pump backplate should be checked to make sure that the components have been installed properly. Once the impeller has been properly positioned, the set screws on the collar can be tightened. This mounts the cartridge sleeve to the shaft. All cartridge seals have some type of device that holds the rotating element in place and keeps the proper amount of compression on the seal's springs until the seal can be installed. This seal uses a rubber bushing, which must be removed before the seal is put in service. The seal installation is now complete, and the pump is ready to be reassembled and returned to service. Well, we've seen several variations of mechanical seal installation, some more complicated than others. While there may be slight variations in the installation procedures, depending on the type of seal you're using and on the equipment that the seal is being installed on, most of the basic steps are the same. One thing that does hold true for all mechanical seals is that they're all susceptible to problems. And in the next segment, which is the last segment in this program, we'll take a look at some mechanical seal failures. Although mechanical seals are designed to last a long time, many seals fail long before their life expectancy is reached. This final segment will focus on some of the reasons that mechanical seals fail prematurely and how to identify causes of common seal failures by examining the seal components. A mechanical seal can fail for many reasons. One of the most common causes of seal failures has little to do with the seal itself. It involves the equipment that the seal is installed on. In many cases, the equipment is in such poor condition that the mechanical seal cannot function properly. As a result, seal failures occur. However, by following the preliminary checks described earlier, the chances of a seal failure occurring because of equipment problems is greatly reduced. Sometimes mechanical seals fail for other reasons, such as the widening of the seal face gap, overheating, material breakdown, and improper installation. First, let's examine seal failures caused by the widening of the seal face gap. As you recall, when a mechanical seal, like the one illustrated here, is in use, the rotating seal face and the primary seal face are separated by a tiny gap. A thin layer of fluid fills this gap to lubricate and protect the seal faces. But if the seal face gap widens, too much fluid enters the gap and the seal leaks. So, for a mechanical seal to function correctly, the proper gap must be maintained. Now, a lot of things can cause the seal face gap to widen, but it usually happens because of a problem with the rotating element. One common problem with the rotating element occurs when the rotating ring sticks to the shaft. The rotating ring is designed to move along the axis of the shaft to compensate for seal face wear and for axial movement of the shaft. Even though the ring can travel only a short distance along the shaft, that movement is essential to the seal's operation. When solids build up on the shaft or spring, sticking can occur. This can prevent the rotating ring from moving properly. Abrasives can also cause the seal face gap to widen. For example, particles, such as those found in some abrasive liquids being sealed, can lodge between the seal faces. These particles could force the seal faces apart, or they could prevent the two seal faces from touching when the unit is stopped. In either case, the seal could leak. The seal face gap can also widen if either seal face becomes distorted. As we saw before, one cause of seal face distortion is over-tightening the gland bolts. Tightening these bolts too much can cause the seal face to warp. Another reason for this distortion is overheating. Heat is often a part of a machine's operation, and mechanical seals are designed to operate under those conditions. But sometimes the heat becomes so severe that the seal parts begin to break down. Severe heat can result from a number of things, such as friction caused by a misaligned shaft, defective bearings, or foreign material trapped in the seal. Overheating can also result from the material being pumped. If the liquid itself becomes overheated, seal components can begin to break down. Overheating can cause the rubber-like materials in a mechanical seal to become brittle and break apart. In addition, severe heat can also increase the rate at which corrosion occurs on metal components. Sometimes the fluid being sealed by a mechanical seal causes problems that aren't related to overheating. For example, seal components may be damaged or destroyed if they're chemically incompatible with the fluid being sealed. The seal parts that are most susceptible to chemical compatibility problems are the O-ring, the bellows, and the seal faces. If the O-ring isn't compatible with the fluid being sealed, it could expand and harden. The expansion of the O-ring may cause misalignment of the seal faces and lead to a rapid seal failure. Hardening makes the O-ring brittle, which means that it could break and cause a leak. The seal faces may also be attacked by the fluid being sealed. One way to tell if this has happened is by examining the seal faces for damage. Since the materials used to make the seal faces are generally corrosion resistant, corroded or pitted seal faces could indicate a chemical compatibility problem. Another category of seal failures involves the installation of the seal. Improper installation can affect just about every component and every aspect of a mechanical seal. One of the most frequent problems encountered during installation concerns the positioning of the rotating element. If the rotating element is not properly positioned, the seal will almost certainly fail prematurely. The mishandling of seal parts before and during installation is another problem that can lead to seal failure. The seal faces are the easiest part to damage because they're usually quite brittle and may be damaged while being handled. Some mechanical seal parts can be damaged as they're being installed. For example, O-rings or bellows are sometimes cut by sharp edges on the shaft, such as shaft shoulders or shaft keyways. The mechanical seal problems that we've just examined certainly don't include every possible failure, but it should give you some idea how many of the common problems arise. Now let's go one step further. Let's see how to identify some of these problems by examining the wear patterns on seal faces. A normal wear pattern on the stationary seal face is seen as an even ring of wear that matches the width of the rotating seal face. The wear pattern should be continuous and centered on the seal face. If the wear pattern is narrow, it could be an indication that the faces are not parallel. It could also mean that the faces are not flat. If the wear pattern is wider than the rotating seal face, it could mean that there's a bent shaft or worn shaft bearings. If the wear pattern is even but off-center, then the stationary element may not be properly positioned in the stuffing box. If the wear pattern is uneven or has gaps, the seal face may be distorted. This could be caused by overheating or by over-tightening the bolts that hold the gland plate in place. If the seal faces are chipped, It could mean that the seal was mishandled. If the faces are chipped only along the inside diameter, there is the possibility that foreign material was trapped in the seal. Sometimes seal faces have a grooved appearance, like a phonograph record. These grooves could have been produced by foreign material trapped between the seal faces. Sometimes cracks are found in a seal face. A seal face can crack for a number of reasons. One of the most common reasons is that the seal was mishandled. For example, the seal face may have been dropped. A cracked mating ring could be an indication that the gland bolts were over-tightened. Hairline cracks found in metallic seal faces may indicate overheating. In this segment, we've seen some of the problems that lead to mechanical seal failures. We also saw how examining the seal components can help identify the cause of the problem. Now, as you've seen in this program, not all mechanical seals are the same. Likewise, not every maintenance department follows the same procedures. The examples and procedures used in this program were general in nature and may not always apply to the seals in your plant. To properly install or maintain a mechanical seal, you must follow your plant's procedures and the recommendations of the seal manufacturer.